we'll call it. Investigate. Report to right. Classification. Import net terms. Take some upon it. any full sure that we transforce mathematically there, because we only want to lose, we only want your output connected. Okay. So level to change fulfilled. Now, what we mean when we the correct input impedance is that if the later, Z, when the loop is connected, and I quite ideal load is connected. The right input, this would be L. Okay. On your the output. What we would terminals. The of the okay, so we just therefore, if this is 50 ohms, we're looking for that to be 50 ohms, ideally. That's 50 ohms. Measured as 50 ohms. Types that are available. And this is here you have and there's a connection at the bottom. Hold on. And then you can have type configuration and pi type configuration attenuators. For obvious reasons, they will be different. A waste of power. I've not been able to compel and choice between okay, unbalanced attenuators. In these designs, is balanced attenuators. To have of what we would expect to be 0. And that's 5 volts. Between the pi type. Unbalanced situation. Your signal stop 0. One of those in the completeness. Attenuate. Top bottom routes. Now, between whether you want and one reason have you're is also 50 ohms or 600. Attenuators. By the way, in your practical, right, that's what you're going to be unbalanced attenuation. Okay. The other type, you had a source that had an impedance of 100. The problem is with that type of design is you have what's called a minimum design. You're always going to get some attenuation. So you say 3 dB. That's the loss caused by matching those two. You can't. Then you may end more than you really want to. But if you really need to match impedances, matching that we know that making the impedance of a symmetrical T design. Z in, by its very nature, Z in, remember what we said about Z in, it's the impedance when the proper load, ZO is a characteristic impedance of this symmetrical design, then we can calculate ZO using that formula there. Z1 squared plus 2 times Z2 times Z1. I'm not going to use an online calculator tool. Modern tools to design your attenuator on that in your a good way of doing it. Okay. So you could check those calculations with these formulae. Okay. If you got the manual formulae, high design, are always more complicated. They're always more complex. So in some ways, that might be why you choose, if you haven't got an online calculator, if you can't get on the, it might be why you'd want to choose to do a T-type design. So there is how you would calculate ZO for a particular pi-type design. You don't want to calculate ZO for your designs. Design to a particular input-output impedance. Yeah, so what you want to find when you're designing is the values of Z1, Z2, and okay. Another thing that could be useful in the field is you have later, but I didn't have any markings on it, and you wanted to know what the characteristic was. You can find out, because you can measure the impedance looking in with an ohm meter. With the load disconnected, Z open circuit. You can measure again in with an ohm meter with the output short circuited, and then use that simple formula there to calculate what the characteristic impedance of that attenuator is. So that's quite a practical thing that could well be useful in the field if you're working with attenuators. Not saying you would be, many of you won't, but that's what you could do. Okay. Of course, what is more likely is that you want to design a particular level of attenuation and have a specific input and output impedance. So we will return, i.e. the calculations required to determine Z1, Z2 and Z3 when we've had a look at how we define the term attenuation, the model and the units for it. So there's what we call the attenuation factor or ratio, sometimes also called, in the terms of amplifiers, we call it the gain. Okay? So the gain is the voltage out divided by the voltage in. So if V out over V in is less than 1, i.e. we're getting less out than we put in, we haven't got amplification, we haven't got a gain, we've got attenuation. So the ratio is less than 1, we have an attenuation. V out over V in gives you that. Okay. So if we're putting 10 volts in and getting 5 volts out, we have an attenuation factor of 0.5 less than 1. Yeah, that would be the gain factor, yeah. A multiple of, so 5 in, 10 out, amplification of times 2. Yeah. We measure gain and attenuation using something called the decibel scale. Okay. In many cases of gain or loss, the numbers involved are very large or very small. An amplifier can easily have a gain, i.e. a gain ratio of 100,000 or more. For convenience, it's better to use a logarithmic scale. So, logs to the base 10 are used, and the ratio is said to be in bells. The bell is a large unit, so more commonly we use the decibel, where 10 decibels is equal to 1 bell. So you may have seen this in hi-fi specification, outputs defined in dB, and noise levels. But if you get involved with health and safety around measuring the noise levels in a factory, then they're usually looking to get it under a certain decibel level. So that there's what's called the power ratio. You're going to have an attenuated design that specifies a voltage in and a voltage out. Your attenuated design software requires you to input the attenuation level you want as in power ratio in dBs. We find that by multiplying the log of P out over P in, so the log of the power ratio multiplied by 10 gives us in dB. And where it is attenuation, what you'll find is that comes out as a negative value. That's telling you that's a negative gain, i.e. negative gain means attenuation. All right? If you have either the voltage or current ratio available, you know what your voltage in and voltage out are, current in and current out are. You can substitute the known formulae for power to that original equation to find what the power ratio is that way. So if you know the two voltages and you know the characteristic impedance Z in and Z out, which for your design is going to be squared out over Z out divided by V squared and over Z in, and if you've got current, so you know the current in and the current out, you need I squared times Z out over I squared. You will definitely need that slide and those, at least one of those formulae, do your assignment work. Okay. So, by example, if your P out over P in is 1, i.e. no gain, no loss, then the dB ratio, if you do 10 times the log of 1, that you get 0, hopefully, on your calculators. If P out of is 100, then you'll get a dB ratio of plus 20. If your P out of a P in is less than 1, in this case 0.1, you'll get the ratio minus 10 dB, meaning a loss of attenuation. There's also a way that you can directly, and voltage ratio in dB, you multiply the log of either I out over I in or V out over V in. So less common to use those, more common in specifications. Let's go back. So, problem definition. So we're going to look at an example problem. Pressure sensor produces a signal of 0 to 20 volts across its rated pressure range when connected to a load impedance of 500 ohms. You need to connect it to an instrument requiring an input voltage of between 0 and 10 volts to an input impedance of 500 ohms. So we're going to have a look at the calculations around that specification and how we can find the values of the symbol resistors needed to make that attenuator. So 0 to 20 in, 0 to 10 out, and 500 ohm. The problem definition is repeated a bit smaller up in the top right hand corner. Calculating the component values manually, the first thing you need to do is find what's called the attenuation factor, N. That is V in of a V out. Notice it's up the other way round. So in this case, N is equal to V in of a V out, because they're what we've been given. So it is 20 over 10, 2. So we've got an attenuation factor N of 2. We also know from the problem, given that ZO is 500 ohms, so now that we know N, we can plug in these two equations down here and find the value of Z1 and Z2. So I'll just pause there and let you do that, then we'll move on. Right, gents, what results we got for that? $666. Okay. So they are the calculations for pi-type design. So let's find using the pi-type time. Again, anyway, it's the same thing. So N is going to be 2. Right, gents, result. As you you're even further away from what your original specification was. What I want you to just do now briefly is calculate for that design dB power that is gain. Well, technically negative attenuation gain, but you never talk about it that way. The use it at a is out because they are different. So I'm going to look at the design of a T-type. So all we need here is one. You're using this for words. Go and find 100 numbers. We build an idea. If you click that with the wheel, you can get that open in a separate page. For some reason, this 5% size. In there is and any other. Yep. You can get 20, 12, 1.2. Between 180. One's under, one's over. Okay, so make a note. 180. We're also looking for 666. So, the number of the beast. We've got a choice there between 680 is over 680 is depends. And that the 560 is the better choice. Okay. Design decisions and what you want. If told that you absolutely must not go for voltage, will give you slightly more attenuation. Maximum, and you again, your design will give you slightly less attenuation. The preferred component. That down 560 or 680 on second value. What we can now do is go back to the calculator and enter preferred values. So what was it? 150 was one of the options, wasn't it? The apparent best option here was 680. So once you have entered in those, when you click calculate, it will recalculate to tell you what your actual dB attenuation is with those preferred values, and it will tell you what the actual system impedance is. So with those two values, with 150 and 680, you're going to get a slightly reduced level of attenuation at 5.7 dB. Okay, we're going to have an input impedance of 482 ohms. ohms. So we're out of matching by 18 ohms. Okay. The other option for the series 180. So we could try that and see what difference that makes. So our attenuation now is slightly above. Input impedance is 20 ohms over. Yep. And was it 560? Even more attenuation, and but only 13 ohms out on impedance, and then the last combination in there is we're 50 ohms out on impedance. See, set a value. I don't want you to go a convenient time. We won't have that at the same time every week. And then when we come back, we'll have a look at the simulation side of this sim. Okay, and perhaps for values, designs, and the simulation of them, and we get time for